Assalamualaikum and hello everyone. Welcome to our group presentation for MAT523, which is Linear Algebra 2. Today, our team is excited to share our findings on a topic that bridges mathematical analysis with real-world healthcare, which is the relationship between age and diabetes outcome. So, let's kick things off by meeting the team behind this work. First, a quick introduction. I am Irfan Zakwan bin Saiful Nizam. Joining me in this presentation and analytical journey are my brilliant teammates, which is Muhammad Azam bin Mohsin and Muhammad Arif bin Muhammad Shahdan. Now, let's dive into this research. Why is it so crucial in today's world? So, in today's global health landscape, diabetes has become one of the biggest challenges of the 21st century. It has reached epidemic levels, affecting hundreds of millions of people worldwide. This crisis is closely linked to the modern life, where rapid urbanization and inactive lifestyles have become common. However, the most important driver is the growing number of older people globally. Biologically, aging introduces complex health challenges. These include a natural decline in the body's ability to produce insulin and a clear increase in insulin resistance, which raises the risk of chronic metabolic conditions. Because older people are more likely to experience fast health decline and long-term complications. Understanding exactly how age affects this illness is more important than ever for modern medical research and public health strategies. So, we are using the Microsoft Azure Diabetes Dataset. This project applies regression analysis to evaluate the relationship between age as X and diabetes outcome as Y, representing disease progression. So we are utilizing both manual calculations and maple commands to determine the best fitting curve. So the table below shows the data obtained.
On to our manual calculation phase. To find the quadratic curve that best fit our data, we begin by setting up our system of equations using the standard quadratic form a plus bx plus cx squared equal to 1. As you can see on the slide, we took our 10 distinct data points and structured them into a augmented matrix. Our main goal here to reduce this matrix using Gauss-Jordan elimination to find a unique solution for our parameters a, b and c. We start the row reduction process by targeting the first column by subtracting the first row from all the subsequent rows. Specifically, using row operation like R2 minus R1 down to R10 minus R1, we successfully create a leading one in the first row and clear out all the entires below it to 0. This gives us a much cleaner matrix to work with as we move forward. Since our original system is inconsistent, we apply the least square method to approximate the best fitting curve. To do this, we use the normal equation, which is A transpose AX equal to A transpose B. First, we do our original matrix A and transpose it to get A transpose. Then, we multiply A transpose by A, which effectively condense our massive 10 rows matrix into a manageable 3 multiply 3 matrix. We did the same for the right side by multiplying A transpose by our factor B, giving us a 3 multiply 1 factor. Once we had this new consistent system, we perform row reduction once again, as shown in section 2 of the slide. After a series of detailed fractional calculation, we successfully isolate our variable. This gives us our final values of A, B and C, yielding the ultimate quadratic regression equation shown at the bottom of the slide. Since our original system is inconsistent, we apply the least square method to approximate the best fitting curve. To do this, we use the normal equation, which is A transpose AX equal to A transpose B. First, we took our original matrix A and transposed it to get A transpose. Then we multiply A transpose by A, which effectively condensed our massive 10 rows matrix into a manageable 3 multiply 3 matrix. We did the same for the right side by multiplying A transpose by our vector B, giving us a 3 multiply 1 vector. Once we had this new consistent system, we perform row reduction once again, as shown in section 2 of the slide. After a series of detailed fractional calculation, we successfully isolate our variable. This gave us our final values of A, B and C, yielding the ultimate quadratic regression equation shown at the bottom of the slide. Finally, we need to evaluate the accuracy of our least square regression line by calculating the error vector, denoted here as a vector E. The error vector is found by taking the actual observed value B and subtracting our predicted values, which are represented by AX in section 1. You can see the step-by-step subtraction, which result in the individual error value for each of our 10 data points shown in section 2. To find the overall total error of our model, we calculate the magnitude of this error vector. We square each individual error component, add them all together and took the square root of the sum. Our final magnitude error comes out to approximately 188.48. This value represents the residual variance and let us know how well our calculated curve fit the actual data trend.
For now, let's get into the Maple calculation. For this part, we first insert the data points into Maple software. The X values represents the age of patients, while the Y values represents of the diabetes outcomes. Next, Maple plot the data points into a scatter graph. From the graph, we can observe the relationship between age and diabetes outcomes. After that, we use the linear approximation command to form a regression model. This model helps us estimate the relationship between the two variables using a straight line Maple calculation. We have to use the right command to get the same answer as a manual calculation. Next, this is Maple command to find the error and magnitude error by using the formula E equals to B minus AX. The last answer for the magnitude error is square root of 123176809984446 divided by 5857107. This value represents the total differences between the actual data and the estimate values from the regression model. Since the error value is relatively small, it shows the regression line provides a good approximation for the data set. In conclusion, this project successfully analyzed the relationship between age and diabetes outcomes using data obtained from Microsoft Azure Open Datasets. By applying the fundamental principles of linear algebra, specifically the least square regression method via the normal equations A transpose AX equal to A transpose D, we construct a mathematical model to understand how a patient's age correlates with their diabetes disease progression index. Both the comprehensive manual calculations and the automated Maple commands yielded identical results for the parameters of our regression line. This consistency underscores the reliability of our mathematical approach, illustrating how theoretical concepts from linear algebra to MAT523 effectively translate into precise analytical frameworks. To evaluate overall accuracy and fitness of the regression line, the error vector was computed using the formula error equal to B minus AX. The magnitude of the error vector E was subsequently evaluated by finding the square root of the summation of the square error for every data point. The resulting magnitude of error confirms that our developed model serves as a strong, reliable approximation for analyzing health patterns across the given dataset. This study successfully achieved all its core objectives, conclusively demonstrating that data modeling via linear regression provides invaluable insight into medical data trends while reinforcing the practical importance of mathematical frameworks in addressing real-world biomedical challenges.